Class, well, today we're going to be deriving equations for the bubble point and dew point pressures. We're going to start off by kind of stating the definition of Raoult's law. I'll get into that now. That is the mole composition of our liquid phase multiplied by our saturation pressure. That will be equal to our vapor mole composition times our total pressure. We're going to do this for two components, component 1 and 2. Make sure you guys can see this clearly. For the second component, same thing, mole composition of our liquid phase multiplied by saturation pressure equal to the vapor mole composition times the total pressure. So before we get into this, deriving it for the bubble point pressure and the dew point pressure, I want to state one thing that is going to come kind of later in my discussion, which is these two, the vapor mole composition multiplied by the total pressure. This is our partial pressure. This is ultimately going to give us a sum that I'm going to get into when I start the bubble point and dew point. So as far as bubble point is when we have high enough pressure and when we decrease that pressure, we eventually see our first bubble of vapor form. That's our bubble point pressure. I'm going to state that and give you the formula that goes along with it. So for bubble point, we have, I want to state one thing. This can either be at constant T or constant pressure, constant temperature or constant pressure. We're going to label this, for this case, as constant temperature. And ultimately, we want to state that the saturation pressure is a function of T. So saturation pressure is a function of T. And then when we get into the equation of bubble point, which is the vapor mole composition equal to the liquid mole composition times the saturation pressure divided by P. So this right here, we mentioned that the partial pressure is the sum. So we want to pretty much state that this saturation pressure, that the vapor mole composition, so the sum of the vapor mole composition is equal to 1. So we're going to replace that with the vapor mole composition and we'll go from there. So 1 equals liquid mole composition times the saturation pressure divided by P. So to finish deriving this equation, we're going to want to solve for P, total pressure. Sum for total pressure gives you pressure equals the sum of the liquid mole composition times the saturation pressure. This will ultimately be our bubble point pressure. Perfect. All right. So going to back this up a little bit as I get into dew point. So for dew point, we're going to want to kind of be saying the same thing. Dew point. That we can either do this at constant T, constant temperature, or constant pressure. For this case, we're going to state the same thing, that we're going to be doing this at constant temperature. Make sure it's clear. So constant temperature, we're going to be kind of saying the same thing, that the saturation pressure is a function of T. So that we can further derive this equation. This one's going to look ultimately a little bit different. We're going to be starting with the liquid mole composition, which is Xi equal to the vapor mole composition times our total pressure divided by our saturation pressure. So as we stated before, the sum of the liquid composition this time is going to be equal to 1. Right? So we're going to want to exchange this value into our liquid mole composition. which is 1 equals our vapor mole composition times total pressure divided by PSAT. Perfect. So in this case, we're going to want to derive for the total pressure. It's going to look a little bit different in this case, which is just going to be our total pressure equals 1 divided by our vapor mole composition, the sum of our vapor mole composition times our saturation pressure. And that will be our dew point. So as I get into coding, I will help explain this in different terms, in more technicalities, to better explain it and kind of be referring to this as we speak as the first homework goes. And thank you.
Cool. So we're going to be continuing off from the derivations of Raoult's law that I did, where we derive bubble point and dew point from Raoult's law. And we're going to continue off of this with the coding section of this. Just to get into a little bit about what's already on the screen, we have the Chemi tools, which was imported from the GitHub site that is going to be getting us these compositions and values that we're later going to use in our lines of code. As you can see right under, we have several things that we imported, such as notebook, props, a numpy as NP. When we later continue our code, we're going to see NP, and that's going to be pretty much imported, and we're just going to be denoting it as NP. Simple as that. And when we get into part B and we get our graphs for benzene, for our bubble point and dew point, we are going to want to import this plotly.subplots that is going to allow that to happen, as well as import root, as we'll see in just a little bit. So to start this code, we're going to want to denote P equal to props of our compositions of benzene and toluene. So the reason why we listed benzene first is because it has a higher volatility than toluene. So we want to put that first. And when we get into our later lines of code and we list the compositions of benzene and toluene, we're gonna denote benzene first, as you can see, because we made it benzene first here. So just to keep a note that these similarities have to continue with our lines of code and it can't differ from line to line. So we're going to then want to define our bubble pressure in our ideal case as the mole composition of the liquid phase at our constant temperature. So one thing I want to say about this is at constant temperature, when we looked at our problem statement, it was referring to it as constant temperature. But when I was deriving this Raoult's law, I did mention that this can be at either constant pressure and temperature. However, in this case, we're going to be looking at it as constant T. So okay. So going to continue on with this code. We have the partial pressure is equal to the mole composition of the liquid phase multiplied by the saturation vapor pressure at our constant temperature. We're then going to define that the total pressure is equal to the sum of the partial pressures that I also kind of discussed in our derivation of Raoult's law. We're then going to want to return these values, return this total pressure as the partial pressure divided by the pressure. Cool. Nice. So we're going to want to list this array of compositions, and it's going to give us these values of our benzene and toluene, and that's going to be Z equals NP dot array 0.3, which is our composition of benzene and 0.7, which is composition of toluene. Like I mentioned before, I know it sounds simple, but because we listed benzene first, that composition has to come first here. It's just going to mess up everything, as well as the fact that benzene has a higher volatility, and that's another reason why we listed that first. So that's going to give us our array. We then want to define our bubble pressure in our ideal case as the mole composition of the liquid phase and then our total pressure. So in this case, we're looking at it as that. Well, that will come soon. First, we want to denote the mixture, which is referred to as Z, and then the temperature of 373.15, which in our problem statement, that is the temperature of both benzene and toluene, the mixture. Cool. So that's going to give us the compositions of benzene and toluene. We're going to later denote some later values and variables, and we're going to see that that has to match up with these compositions. So just to keep that in mind, we're then going to define our bubble temperature in our ideal case at the mole composition of the liquid phase at our constant pressure. We're then going to want to define our deviation pressure at constant temperature. And then return this value, return this bubble pressure in our ideal case at the mole composition of the liquid phase at temperature. And that is going to replace that value that we're going to denote here as 0 minus our pressure. We're then going to want to label T is equal to temperature is equal to the root, which is pretty much just a solver. And that's going to be the deviation pressure and that's going to be our deviation pressure. Cool. So we're going to return this temperature at the mole composition multiplied by the saturation vapor pressure at our constant temperature divided by our total pressure. T equals rho P. $300. Trying to look at my ear right now and see what happened in this case. Here, returning our temperature, multiplying. Oh, silly me. Cool. All right. So after this, we're gonna want to find our bubble temperature, and that's gonna give us our final composition answers as well as our temperature. In this case, though, we're not going to label it as 101,325, but we want to get close where that value is going to reflect that actual temperature of 373.15. I found that 105,789. I believe will give us the closest value. So let's see. Yep, there you go. So 373.149. And if I tweak it here a little bit, when I was playing around with it, I thought, let me see if I can get closer, right? So you see this is just a tad bit off. Now I'm curious if we start adding fraction there. So that will give us the closest value. So 0.53, 105,789.5 pressure. That's going to give us our 373.1500. That's going to give us the temperature here that will also reflect that temperature here, as well as our compositions that match up with the compositions here at 51.51 of benzene and 0.489 of toluene. We also want to see that this bubble temperature, this bubble pressure, when we decrease the pressure enough, when we decrease that temperature enough at a high enough pressure, we're going to see that turn into a liquid, and we're going to see that liquid turn into that first bubble of vapor form. And that's how we denote the bubble point as a bubble point. Right, gonna pause this and continue the next line of code. Okay, so continuing part A of homework one, as we did previously, we were finding the temperature and pressures of our bubble point using our given information. They gave us compositions, they gave us this temperature. So we're basically going to be replicating this and doing it for dew point. Just to recap on what we did before, right? We were kind of estimating a pressure. What was initially even kind of what we did in class, right, was at 101.325, that standard number, right? And just doing a little bit of tweaking, getting it pretty exact. Um, I was able to get our temperature at exactly 373.15, kind of just trying to estimate as close as we could get along with our compositions of benzene and toluene. All right, so I'm going to continue and do this for our dew point pressure and temperature. We're going to first want to define our dew pressure in our ideal case for the vapor mole composition. Instead, this time we're talking about dew point here. So vapor mole composition, and like before at constant T, gonna want to state that this pressure is equal to the inverse of the NP dot sum. So the sum of the partial pressures at Y slash vapor mole composition slash our total pressure dot P dot P divided by P dot P VAP, right? So saturation vapor pressure at constant T. Okay. Cool. So gonna want to return this value at our total pressure. I want to return this value, our total pressure, and multiply our vapor mole composition multiplied by the P dot P VAP that I mentioned before, our saturation vapor pressure at constant T, right? No, do not erase. Okay, constant T. Okay, shift enter, make sure it's messed up. Okay, gonna continue off of here. We're gonna want to state that the dew pressure of the ideal case at our mixture of benzene and toluene at 373.15, that standard temperature that we've been consistently referring to, and we get this array, right? We don't have to state this array again. We did it previously, so it's gonna give us that array of our pressure in pascals right here, as you can see. And then we got our mole composition. Yeah, got our compositions. Okay. Okay, so found an odd error where these mole compositions are not mole compositions, right? So just look through the error, and it was then deducted that this is not correct here, right? So what we do want to do is divide this y times pressure divided by P dot P VAP. See what it does there. Okay, perfect. So we got our mole compositions that we are actually looking for. Cool. So going to continue off of this and define our dew temperature this time. Looking for temperature in this case, in our ideal case, and again, vapor mole composition at our constant pressure this time. Okay, gonna want to define this deviation pressure at constant T, then return this value. We're gonna want to return it to our dew pressure in our ideal case of our vapor mole composition of our temperature and return that 0 and subtract it from our total pressure. Same thing as we did previously. Code looks good. Let's continue. So doing the root solver, we can continue this on the next line of code. So gonna label temperature and then input root, which is really just our root solver. And then we have our deviation pressure, and then just going to be estimating a number. In this case, we're going to be just using 300. You could do 350, whatever, something that's relatively close. But again, just estimating a number. Okay, good. All right. So we're then going to finally want to return this value at our big T temperature at our vapor mole composition times our total pressure divided by P dot P vap. P dot P vap at our temperature. Looks good. Okay, so now we're gonna wanna now get that temperature at our dew point, right? So we're going to state that the dew, we're gonna want to say that dew temperature, right? So pretty much the inverse of this, so dew temperature in our ideal case is the mixture of this number right here. We're gonna want to input this number in Pascal, which was 89001 .789. Try to get as accurate as we can, right? Cool. So there you go. Perfect. We mash it up. Relatively close, 372.81. We got our mole compositions, 0.15, 0.85, and it looks good to go. I'm gonna start now doing the graph parts of the bubble and dew points, continuing on part B in the later part of this video. Thanks, guys.
Of y1 versus x1 using our relative volatility constant. So just to start off, we're going to be starting off with our two component system. So that's going to be x1 p1 sat equals y1 p, and our second component is going to be x2 p2 sat equals y2p. This is pretty much using just Raoult's law. This is our two components. Perfect. Okay, so before we get into this, we want to first start by saying what is K1, what is K2, and what is alpha. So K1, K2, and then alpha. K1 is just going to be y1 over x1, and K2 is just going to be y2 over x2. And then our alpha is going to be K1 over K2 in this case. Okay, so y1 over x1, we're going to state that as p1 sat over p, and this is going to be p2 sat over p, and our alpha is going to be p1 sat over p2 sat. So notice how the p's disappear. That's pretty much what's going to happen here. So we can also denote x2 as 1 minus and y2 as 1 minus y1. So let's do that. See everything? Cool. So this is going to be 1 minus x1 p2 sat equals 1 minus y1 p. So combining these together is going to be x1 over 1 minus x1 p1 sat over p2 sat, and then equals to y1 over y2, y1 over 1 minus y1, and then our p's are just going to cancel out. Okay, cool. So one thing we can say is we can denote this as our alpha, so as this constant, And before going into deriving this and solving for y1, I'm gonna go into Clausius-Clapeyron's equation, and we're gonna go ahead and we're gonna derive that. So we're gonna say that Clausius-Clapeyron equation is ln p2 uh, ln p2 for second temperature over ln p1 t1 equals the heat of vaporization over r, and that's going to be 1 over our first temperature over 1 over second temperature. So looks good. Okay, so we're going to continue to derive this expression. We're going to want to say that ln of P1T over 101.325, that's our just pressure in pascals, equals our heat of vaporization over our constant, and that's multiplied by 1 over T1 over our first boiling point pressure minus 1 over T2. We're going to want to do this for pretty much just the second component. It's just T. So ln P2T over 101.325 equals our heat of vaporization over R, and that's going to be multiplied by 1 over our second boiling point temperature minus 1 over T. So we're gonna want to go ahead and combine these and pretty much subtract it from each other. So let's go ahead and do that. So it's going to be P1T over P2T. As you can see, everything on this left-hand side pretty much cancels out except for these P1 over P2Ts. That's going to be equal to, sorry. So that's going to be equal to, see good, our exponent of 1 over our R, and that's going to be multiplied by our heat of vaporization 1 over our first boiling point temperature minus our heat of vaporization 2 over our second boiling point temperature. We're then going to want to add the second half side of this. So it's going to be adding 1 over R multiplied by our heat of vaporization 1 just over T minus our heat of vaporization 2 over T. Cool. So that concludes that part, and then we're going to want to go ahead and derive this y1. So to continue to go ahead and derive this, we're going to want to get y1 by itself. So x1 over 1 minus x1 multiplied by alpha is going to be equal to y1 over 1 minus y1. So we're going to want to get y1 by itself, so we're going to move this 1 minus y1 to the other side. So we're going to get 1 minus y1 multiplied by alpha multiplied by x1 over 1 minus x1, and that's going to be equal to y1. So from this, we're going to want to divide out and factor. So what we're going to get after this is we're going to get alpha multiplied by x1 over 1 minus x1 is going to be equal to y1 multiplied by 1 plus x1 over 1 minus x1. Right, so after this, we're going to want to divide these out by each other, and then that'll be it. So first start, got this alpha right here. It's going to be 1 plus this. After we divide this out by each other, we're going to get y1 equals alpha multiplied by x1 over 1 minus x1 divided by 1 plus x1 over 1 minus x1. So this is going to get our y1 equation, and we can go ahead and start coding from here.
Okay, so we're going to start part B of homework 1. Going to continue off of what I left off of. To get into a little bit about this problem statement, We're gonna first assume that benzene and toluene are gonna behave ideally. We're gonna write these codes to generate the dew and bubble curves. Then we're gonna make a plot of y1 versus x1 at our constant pressure, and then derive these expressions using the whiteboard and using that fixed relative volatility. We can compare these results, what we got over here in part B, part two. Cool, let's get into it. Okay, so to start off, we're gonna say that z our z's are gonna equal lens space, np dot lens space, numpy dot lens space at from 0 to 1, and we're gonna be saying this for 20 points, 20 data points. Okay. We're then gonna say that our z's are gonna equal np dot c score. And then this is going to be from Z1 and then 1 minus Z1s, I believe. Okay. All right. See, there you go. All right, cool. First try. So we're going to define this array. It's going to put this array from 0 to 1, benzene and toluene. It's going to give us all of these composition data points. And then it's going to leave off from benzene at 1 and then toluene at 0. Cool. Let's move on from here. Now we're going to be kind of defining and stating these empty arrays. We're going to start at our x1s are going to equal this empty array here. Our y1s are going to equal this empty array. And our p's are going to equal this empty array. Okay, so we're going to state that our temperature is equal to 373.15. Pretty much what we've been using from part A to part B. This is our temperature at benzene and toluene. So we use that to calculate these bubble pressures, bubble temperatures, and now we're gonna do it when we create these dew and bubble curves. So it's pretty much symmetrical all around. We're gonna put in a for loop that's gonna say that for z and z's, and then we're going to state that P is going to be y equals our bubble. Give me 1 second. Okay, so continuing off of where we left off, we're gonna state that the bubble pressure that for the ideal case at Z for all of our components at temperature, right? Then we're gonna enter all of these X's, the Y's and P's, and we're gonna plug this back into these first three arrays, right? So X1s are gonna be equal to you're gonna want to append this. So X1s is append X0. We're gonna append our Y's. So, and then we're gonna append our P's. P's dot append. Then we're gonna state this for P. This pressure right here. When we created that for loop. Okay. We're now gonna start to create those subplots for our bubble and dew curves. We're gonna start by saying that fig equals make underscore subplots. Zero. Then we're gonna say that fig dot add underscore scatter is from x equals to our x1s and y equal to our p's. Okay, so we're gonna name this bubble And when we make the next one, fig that odd underscore scatter. Let's say that x is going to be equal to our y ones. That our y is still going to be equal to our p's. We're going to name this do. Okay. And quick mistake. This is for our z's, not our x's when we're appending. Okay. We're gonna fig that add. Okay, we're gonna be making statements to state our width and height. So fig that add underscore fig that add update score layout is gonna be for our width. It's gonna be equal to 400. And then let's do this. And then height is gonna be equal to 600. I think it was the other way around. 600 and then 400. We're going to state this template as equal to Plotly. So Plotly underscore dark. And then state that our title is going to be equal to our benzene and toluene. How do I write this? It's going to be F dash benzene at 1 divided by toluene at 2. And then our T is going to be equal to T. Okay. Hmm. Okay, so starting from where I left off, sorry, let me delete some of this practice runs I had. Yeah, so I kind of had to I left off from here, and the mistake I made was these were actually brackets here. They were supposed to be parentheses, so I changed it to parentheses, and I was finally able to get this graph. Um, and as you can see here, everything under this dew is going to be our liquid. Anything above this bubble line is going to be our vapor, and then we have our vapor liquid equilibrium, right? So I'm going to do this the same thing, but instead for pressure, I'm going to create a plot, generally the same plot that's somewhat similar. And one thing I want to note is I actually had to buy Zoom Pro because I wasn't able to um, make videos longer than 15 minutes, or at least I don't know if there was any way around it, but I ended up purchasing the Pro and it was kind of annoying. I had to break up the videos into so many parts. So hopefully gonna try to keep it in more than one in just one video because I know once I get to editing, it'll be kind of tough to manage it. Okay, so continuing off of this, we're going to be doing relatively the same thing. So x1s equals our empty arrays, y1s equals our empty arrays, these equals our empty arrays. So, or this is going to be t's in this case. For time's sake, let me just copy this. What we're doing is just changing all the t's and p's and p's and t's. Um, so, okay. Cool. So what we want to do is change this pressure to 101,325. Change this T, bubble P, bubble T ideal, Z comma T to pressure. Change this into our T's dot append. these, and this last part. Double check it. I think this is pretty much it, what we have to change for this. Let's go ahead and graph it. Perfect. Okay, so same thing like we did before. This dew line, however, is on the other side, and this is everything here is going to be liquid in this case, and everything under here is going to be vapor. And again, we're going to have our vapor liquid equilibrium. Okay, let's go ahead and plot our y's against our x's, and in that we're going to say that fig 3 equals make underscore subplot and our empty array. Say fig 3 dot update underscore layout x equals x1s and y equals y1s. So the same thing, fig 3 dot update underscore layout. We're going to say that x is equal to bracket 0 dash 1 dot, and then comma y is equal to same thing 0. Okay, so fig 3 dot update underscore layout and equals 400, or width equals 600, and height equals 400. And again, we're going to name this template equal to plotly underscore dark, same as we did up there. Name underscore fig 3. What? Just fig 3 equals make underscore sublot empty array fig 3 dot update underscore layout x equals x1s and y equals our y1s. Do we have a comma there? I believe we do. X, something's wrong with that line. Okay, so what I messed up here is I realized that we've been doing that fig dot add underscore scatter. We were not updating the layout here. Fig dot add underscore scatter. Oh, it's saying something's wrong with this line. Yeah, this is going to be fig 3 dot add underscore scatter also. Layout. Perfect. Okay, so as you can see here, we have our equilibrium line and we have all of these points. And if any of these points hit this equilibrium line, we're going to have the azeotrope. So yep, that completes that part of it. Okay, so continuing the rest of this after my derivations, I'll try to include that right before this. When I cut through the video and make the edits. But let's go ahead and say that our saturation pressures, we want to define those. So saturation pressure, this is going to be all from the GitHub site. So P1 sat equals P dot P vap at 373.15, the temperature that we've been consistently using. And then we're going to say alpha, that's denoted as relative volatility. So we're going to say that alpha is equal to P sat T PSAT 1 divided by P1 sat divided by P2 sat. Yeah, actually, let me change all of these to this. One set, P2 set. Okay, cool. Okay, so now what we're gonna want to do is we're pretty much creating like another plot like this with the points that come go all across this. So the way we're gonna do this is let's copy and paste this right here. Copy paste this. We're gonna change all these fig threes to fig fours. We're gonna add another line, and that's gonna be uh, fig four dot oh, fig four dot add underscore scatter. I say x is going to be equal to our x1s. Okay, we're going to pause this part of code. I missed one thing. So we're going to define, we're not going to want to equal these to our x1s. We're going to want to equal them to our x1 plots, which is pretty much plotting those x1s and y1s. So we want to define those. So we're going to say that x1 plot is equal to numpy dot linspace 0 to 1 to 50. And then we're going to want to say that our y1 plot is equal to alpha, that relative volatility, multiplied by our x1 plot divided by our 1 minus x1 plot. Let's resume this. We're going to want to say that we're going to divide this by our 1 minus x1 plot. We're going to add that to alpha times x1 plot. Let's put the appropriate parentheses here. Okay, so continue off of this. I did lens space here, so just typing error, that should be good. Okay, so let's see this. What we're gonna want to do here is we want to say that x equals x1 plot, y is gonna be equal to y1 plot, and then we're gonna have mode equals markers. Perfect. So this is what we wanted to look like. What markers did was pretty much enabled us to mark all of these points. And that concludes homework one. Let's go ahead and finish off of that. And thanks. Thank you.